and welcome back to our week revision of 7th and 8th. Before beginning, my small introduction. Myself, Dhruv Janakala, and I'm your maths mentor. And this is a page distribution. You can use it while accessing the notes. These are the topics that will be covered in today's lectures, starting from basic topics like previous functions that we have came across. Then we will go through functions in one variable, some graphs and tangents theory, limits for sequence, limits for functions of one variable, limits and continuity, differentiability and the derivatives. Then we will come across derivatives and L'Hopital's rule. Also, we will be covering some other summary of derivatives, tangents, and linear approximations in these lectures. Starting with basic functions. Functions are relations of input to output which can be written in this form function where x stands for domain and y stands for range. This means that some values of x are mapped to y as the input and output. Your domain is x, codomain is y, and the part of the codomain that actually is in play is called the range. Now what the word monotonicity means here? This means that your function is either following strictly one path only, either it is continuously increasing or it's continuously decreasing. That's called monotone nature of a function. Like how straight lines are. They are either decreasing or continuously increasing. As you can see here, these are two examples. F1 of x is a increasing function and F2 of x is a decreasing function here. These are monotone functions which do not change. These are some other functions that we came from linear functions which represents straight lines in the graph form, which are from real numbers to real numbers, then quadratic functions which are from real to real numbers, but they show a parabola in their graph. Then comes the polynomial functions, as we have studied in week 4. These functions form different types of graphical shapes, such as ellipse or let's say hyperbola, parabola, and then it can be any sort of graph or it can be a different graph also. These all are polynomial functions. There are other two functions, exponential log functions, which can be represented as a to the power x and a log x base a. These are the graphical representation of functions showing how growth is related with its slope. As you can see here, 3 examples of 3 different tangent lines are given. The one which has the greater slope is the faster decreasing or increasing function. Let's say here you can see the y equals to x to the power 2 climbs up quickest. That's why this is the most fast growing function, whereas y equal to x square is the slowest function among these 4. So you may say that the fast growth is directly proportional to the slope of the function. As the slope increases quickly, the function will be fast growing or fast decreasing. Fast decreasing when the function has a negative slope and its slope is greater and function is negative. Then these are all the formulas of trigonometry. All are not necessary, but you may go through them, which will be in the PDF file. These are the functions of one variable like sin x, cos x, cosine x, tan x, cot x. In this, the main things you need to keep in mind is that your sine function, which comes from 0 to 2 pi, cosine functions 0 to 2 pi, but there is a step gap of pi, half pi. You see, it starts from 0, whereas this starts from 1, which means that it's moving pi by 2 steps ahead or behind, as you said. Then there are cosine functions. These are parabolas like structures which are reciprocal of your sine functions. Then there are sec functions which are reciprocal of your cos functions. Then there are tan functions who has period of pi, and also these functions are more like cubic functions, and these are the reverse tan functions, or you can say cot functions. Then we will come here, graphs and tangents part. 2 terms to keep in mind is exponential decay. It means that when your graph falls down too fast, like as you can see here, your graph starts to fall like this, and by reaching its other peak, it gets closest to 0. As here you can observe that it is shown as it coincides, but it actually never coincides with the light. It keeps on decreasing, but never actually coincides with it. It's something like this, if you will zoom in Micromax. Then this is the normal distribution. These are the equations. This is the exponential decay equation, and this is the normal distribution. Also, we will see that this convergence to E. We will go through it in the next slide. These are some theory topics about graphs that you must know. Firstly, a curve is nothing but the path through moving points. Multiple variable points make a curve, which are called as functions. These curves may bending at various places, like they have different curves as you have seen. This is a curve of x cube. This is a minus x squared type of graph. These parts are the bending parts here. Then tangent lines are the line which just coincides with the curve at a particular point. Let's say this is a curve, and let's say here you are passing a tangent. So this point is a tangential point where a tangent T cuts on a point P on the curve C. These are tangents. First, it was thought that the line just touches the tangent curve. Tangent line just touch the curves and pass. But when you will go through calculus, you will observe that the line actually coincides with the curve at particular points. Then another thing recent is just that how tangent lines are defined, and an example of tangent lines. Moving ahead. Here are limits for sequences. These are the rules we have to follow regarding the convergence of sequences. First, whenever you have a n as your equation, it will always converge to a, which means that for every subsequence of an, it has to converge to a. Same, if an converges to a and bn, these are the functions. Bn converges to b, then sum of an plus bn will converge to a plus b. Same, if an converges to a and c it belongs to real numbers, then you can multiply it on both the sides. It's just like a summation. You can multiply or remove the common part out on both sides. Then if this addition same applies to subtraction also. Then we will same it's applicable for multiplication also here. An converges to a, bn converges to b, so an times bn converges to ab. It's just like you have given an equation and then said it converges to 0, and you have another equation and it converges to a, let's say. Then both the equations when multiplied should converge to 0. That's how it means. And if two different equations converge to two different constants, then multiplication, addition or subtraction of this equation should be identical to their multiplication, subtraction of addition of their constants. Then let's say n converges to n, f is a polynomial function 1 real bit. Then we will substitute an's value in function. It will be equivalent to substituting the convergent value of a in the function. In the sixth still you can see. Then when an converges to a and when c belongs to real number, then you see that c raised to a convergent, c raised to a function is also similar, converges to c raised to the convergent. Let's say you have a function x which converges to 0. Then that means that when you will take a c raised to x, then the convergent means c raised to 0. Also, ninth rule, if an converges to a and c belongs to real numbers such that an is greater than 0 and a comma c are greater than c, then log of an base c converges to log of a base c. Then the sandwich principle. The functions converges to a same constant, then there is a cn in sequence which is lies between a and bn, and also it will converge to a. These are some more convergent and divergent sequences. This all will be directly applicable. You just have to know this all. And in variable equations, you have to substitute. Then these are some special. Let's say you have a sequence n, then it is divergent. The reason is because when you will take this, it will not, let's say summation of n numbers from 1 to infinity. It will go towards infinity, and infinity is not a constant. That's why it's a divergent. Minus n converges to minus infinity. That's why it's a divergent. Then when x belongs to real number, then the sequence is summation of xb upon k factorial is convergent. When you will solve this, you will see that it converges to e to the power x, which is a constant based on x. Then it's the same for 1 plus x upon n whole raised to n converges to e to the power x same. Most of the sequences that we will be having either will converge to e raised to s, or some constant values, or maybe it converges to zeros or 1. Now here, for we all know that we have what are sequences. Let's say you have an is a real sequence of real numbers. That means that when you will write all the terms of a function, then all of them after summation should go towards a particular value. It can either be a countable or uncountable. If it's a countable like 0, 1 or some constant value, then it's convergent, or else the sequence are called divergent sequences. These all are different types of symbols used to show convergence. Here you can see definitions of convergent and divergent are written. In simple words, I said that convergent means your equation after summation of multiple values should come at a point of constant 0 or some value of constant. Divergent means that it should either be uncountable or it should be so uneven that it cannot be calculated. Minus 1 to the power n. You cannot actually not depict what will be the answer. It depends on n. If n is a positive, then your answer is 0, and if n is a non-positive, means a non-even, then it will be negative 1. That means there are two possible values, which should not be a case in convergence. That's why it's a divergent. Next topic is the limits for functions of one variable. To begin with, we will see what is continuity of a function from a given point. Here, we know that any function after applying limits can give its value at that function. That function and a point A at which the function is to be calculated such that the an converges to A, where an and A belongs to the domain of the function. In that case, we can write them as limit of function x tends to A, which means that where the function converges to A gives function's value at A. Here are some other examples of limit. Limit when x tends to 0, sin x upon x is equals to 1. Here x and x can be anything like given zeros. Sin of something upon something equals to 1. Same limit when x tends to 0, 1 plus log x or base e whole divided by x is equals to 1. This means that this both converges to 1. Here is something that you should be keeping in your mind when you are using substitution to find the limits. In this case, you should substitute the value only after you have completed your derivatives. Let's say in this example, first you will derivate the equation, which is your answer will come 2 here. So you won't apply 2 first, because in that case you will observe that this part, the denominator will become 0 and anything upon denominator will be 0 or becomes undefined. That's why first you will calculate and then substitute the values. Next, whenever your x tends to plus or minus infinity, these things are to be kept in your mind. Let's to have a sequence xn diverging to infinity. Sequence x1 diverging to infinity. In that case, let's say you have a limit exists such that the function's value at fn converges to the limit. And this implies that whenever the limit exists and your x is increasing, then your function's value is equivalent to the limit, which means that x is directly proportional to the limit. And when your x value is less than n, then in that case you can say that your sequence diverges to minus infinity. Here also limit exists, and when your function, you'll substitute the xn in your function and try to calculate, it will go to the limit. In both the case, you see both of these are divergent, and your limit when x tends to infinity, then to it's equals to limit, and when you will substitute limit x tend to minus infinity for a function, then also it will is equivalent to limit. As we know that in previous we have learned that function's limit can be tend to the limit itself at a particular constant. Here you can see there are three ways to calculate limit. First, you will see the position. Let's say this is a graph. In this case, this is your point. So there are three possible limits to be verified. First, the limit on the point, it should be equivalent to the limit to just side of the point, and then it should also be equivalent to the limit just left to the points. When all these three limits are same, then only your limit exists. These are example how to find the limits of left. It's the same. Here example is given. Let's say you have a function which gives 1 as a value if x is a rational number, and it gives 0 if x is not a rational number. Therefore, you can take a value of 0, which is a rational number, which gives the value of 1. Whereas just to the left and just to the right, both here, two irrational numbers are present. One is negative x, let's say, and here it's x. In both the cases, you will get the value of 0 and here also 0. That's the reason why you can conclude that these 3 points, even when lying so close that they overlap each other, they don't have same values. That's why the limit doesn't exist, because at the value of 0, it has a break. It's something like this, the graph. This is the open point here. All rational numbers will be open in this graph. Something like this. These are points of rational numbers. And between two irrational numbers, there are the number of irrational numbers are there which are not unique. That's why if you take a very close point, then here you will find that your numbers are irrational. That's why your limit doesn't exist here. Now here are some continuity regarding the functions rules. Let's see, you have a function which has a limit where x tends to a. In that case, that function is equals, limits of function is equals to f. Similar you will do for fx, gx, and then when you will sum that function, the limits get sum. Same as before, the constant multiplied comes out. Same goes for subtraction and also multiplication. And for Division, the only rule is that the gx should not be equal to 0 because then it will become undefined, remaining stays the same. That sandwich theorem, as we have studied before, when let's say two limits of function fx which is L, and then you have a limit of function gx which is again L. So in that case you can say that let's say there is a hx which is between fx and gx, then the value of hx is also equals to L due to the sandwich principle. Also, a point to be any function to be continuous, it should have existing limit at that particular point where continuity is to be tested. This is a graph of a discontinuous function. As you can see here, the limits gets broken at multiple places. That's why here continuity is not present because the limits are different, and at some point the limit doesn't exist because of the breaks. Whereas in a continuous graph you can observe that limits always exist at any particular point you can test it, and that's why it's continuous. Some examples of polynomial function, rational functions with non-zero denominators, then ex log of x base anything, then x greater than 0, sin x cos x. These all are continuous functions. These are some examples. You can take and solve them. Then differentiability and derivatives. Differentiability and derivatives come with the idea of rate of change. Let's say in a very small amount of time, how much the matter or the particle is actually changed from its ideal position. That's how you take, let's say you have a curve, or let's say you have a parabola and there is a tangent passing to the parabola's vertex. At that point you will see that you will observe that only a point is being cross intersection of parabola and tangent. But when you will apply derivatives and you will zoom in, you will find that an entire region is being placed which is overlapping under them. You can verify it using limits. Some of the questions which can be used to calculate, let's say you have a truck travels with a speed of 2900 kilometer distance and it takes about 72 hours to travel that. So in this case, whatever speed you are calculating is nothing but the rate of change, which is nothing but derivative of it itself. Moving forward, differentiability. Let f be a function defined on an open interval a. Then the function is differentiable at a if limit exists. And to calculate the differentiability of any function, you can use this formula. Let's see, you can take any h value here, h tends to 0, not necessary. You can take any value of h if you want. And then you can solve for this. Let's take your function is x square. So in that case, here you can see an example has been taken. You have a function, then derivative of the function will be in such a case. If you take it at x square, then x plus h whole square minus f of h, which is x square upon h. When you will solve this, you will get the differentiated value of the function x square. And at the last step, you have to substitute h equals to 0 because after first step, when you will open the h square, then h will get cancelled from denominators. So that's why your equation from being not defined will become defined. Here are some rules about derivatives to be keep in our mind. First, let's say you have added two different functions, x square and x, which will become x square plus x. And you need to see what is the derivative of their sums. Then you can directly take derivatives of individual and then add up. It gets applied to addition, constant multiplication, and also subtraction. But the product has a different. For product, as you can see here, this is the derivative equation. Product rule using which you can derivate any two functions which are in product. This is the quotient rule. In this case, first you will derivate the numerator, then multiply it with denominator, then you will put a subtraction sign, and then you will keep the numerator as it is, and then you will derivate the denominator, and then you have to divide it by the denominator's function square. This is a chain rule. Whenever you have to you have a function in composite functions are there. Let's say you have x square and x cube. Let's say you have this is a fx and this is a gx. In that case, you have to find the f of gx, and then you are asked to take derivative of this. In this case, you will first do the derivative of outer function, which is x square. After derivative will become 2x, and substituting, you will substitute cube here and then multiply with the inner derivative, means x cube derivative is again 3x square. So this your final answer will become 6x5, whereas your actual derivative was 6 to the power x to the power 6. This is your derivative, and you can also verify that you know that x to the power 6 has a derivative of 6x to the power 5. That's why it's correct. It's called chain rule. These are some examples. You can use them. Indeterminate limits here. In this case, we will use L'Hopital rule. Let's say you have an equation of a function which you, after taking first derivative, you didn't get a proper solution. Then you can take the derivative of only the part of the function which doesn't give you a satisfactory solution. Let's say you have a limit log of 1 plus x upon x. In this case, you can see the limit tends to 0. That's why you will simplify this and you can write this as 1 upon ln of x. And then when you will take it, then you can directly take 1 upon ln of x upon 1 will become 1 upon 1 plus ln 1 plus x. This is because you know that limit of a log function upon the same log function of 1 plus x upon x is equals to 1 itself. That's why. Here are examples of them. Let's say in this case, after first derivative, you get 2x minus 5. Here you can, then you can directly take. Here you don't have to, you know that sin x upon x is directly 1. In this case, you will use the L'Hopital rule. After derivating this, you observe that you get the value of constant b upon d. Here 1 minus cos x after derivating becomes sin x. Here you can see that the above part is sin x by trigonometric ratios and the lower part has been derivated. Then you will get the value of 1 upon 2. But this is the last topic of the lecture. Tangents as a limits of secants. As you all know that secants are specific curves and then tangents are nothing but the derivatives of these secants. Every curve has a derivative which refers to a line depending on their degrees. Then comes here the linear approximation topics of the curves. You can find the linear approximation means where the approximation of the entire equation will lie. You can keep this equation in your mind, which is the linear approximation at any function is equals to the function at a constant plus function's derivative at the constant multiplied by the x minus a function minus the constant's value. As you can see here, this is nothing but the function at x plus function's derivative at a and then function's derivative at x minus a. This is what it means by linear approximation. So that's all, guys. Thank you.
Free audio post-production by alphonic.com.